Hi, Yasmina. Thank you. And hi, everyone. So, Ruby rock and roll. The topic of today is going to be about music. So if you are someone who's interested in music, this might be something that you might want to take special note. Essentially, what I'm going to talk about today is how you can use Ruby to create music. Before we begin, I want to talk a little bit about myself. I work in a company called HP, so I'm quite sure most of you, if you are in the IT industry, you would already know HP. But I work in an organization that's a little bit less well-known, I suppose, amongst all the other things that HP is well-known for. I work in an organization called HP Labs. HP Labs is a global and it has 7 sites, the latest being in Singapore. We started in 2010, and we have been doing a number of researchy things. But the one that we specialize in Singapore is on cloud computing. Of course, cloud computing is not what I'm going to talk about today. And I'm going to talk about Ruby primarily because that's my passion. And it has been my passion for the past 6 years or so. I've been programming in Java for about 11 years before that. So I switched over to Ruby about 6-7 years ago, and I sort of never turned back. I've even written 3 books on Ruby. The first being Ruby on Rails web mashup. That was on Rails, obviously. The second one was cloning internet applications with Ruby. That was a change, actually, from Rails. I switched to using Sinatra at that point in time. Still web applications, still about building web applications, but no, not Rails anymore. The latest is, of course, the reason why I'm here as well, is exploring everyday things with R and Ruby. And that is purely not anything to do with web applications. That's basically about using Ruby and R, a little bit of R, to explore the world around us using programming skills that I hope all of us are familiar with. Hopefully, the book might be of interest to you. Yasmina is going to talk about it later on, but we are having actually a sale deal today for this book. Okay, that's enough about myself. Let me start the topic now. So Muse is a domain-specific language for creating music, and this is the URL to the GitHub repository. The code is open source, and feel free to download it and check it out anytime you want. I mean, even during this presentation. So, what's so special about a Ruby DSL for creating music? There are already gens out there, but this particular library that I'm using, or that I created, it's not like any of the others. Many of the other Ruby libraries out there today create music through creating MIDI files, and these MIDI files are in turn pumped through your computer or pumped through synthesizers, and they will produce music. Muse does not create MIDI files. It actually creates WAV files. So it creates binary music files that can be played in a music player, right? And this is something rather different from the existing gems out there. There isn't any specific reason why I would want to do that, but it's something interesting because I'm generating the music from first principles. And you'll see soon in a couple of slides down the road. So before we begin, I want to share a piece of music with everyone. Those who are of a certain age perhaps would recognize this piece of music quite immediately. Okay, the music is not coming out. Let me switch it on. switch on something. I need to turn on the music. Sorry. You notice the structure behind the scenes. You will probably recognize the music. Okay, there was a short clip from the Eagle song, Hotel California, a song that was actually transcribed from the original music to Muse. And I'll show you a little bit of the music itself, the score itself right now. If you just give me a second. So this is Hotel California. You can see right at the top that I'm requiring the library. And then I go on to define the music, Hotel California, defining the chords, the intro riff, and the subsequent musical notes, so on and so forth. I'll go back into this in a short while. Let me get back to the slides. Okay, so what will we be doing today with Muse? So first thing is I'll talk about creating sound because, well, music is sound. Specifically, I'm talking about how we organize sound into musical notes. And then I'm going to talk a bit about writing those notes to files, and finally wrapping it around with a domain-specific language. About sound. Sound, it's from principles of physics that you probably learned in school, is produced by vibration of something. And this could be air, it could be water, and so on. Vibration produces waves, and the waves has properties that include things like amplitude, which is basically volume, as well as frequency, which is pitch. And the higher the amplitude means the louder the sound, and the more cycles in a second means the higher the frequency. Now, how this is important, we'll see in a short while. How do we make a sound? The sound is produced by sine waves. And if you have a pure sine wave, it is basically pure sound. And if you want to create any other type of sounds, what you can do is you can produce different sine waves that are combined with each other to produce a completely different set of sounds. So to create a digital sound, we would generate the digital sine wave and then put them into with a sound files. And this is what we are going to do in Muse. Let's move on to music now. So music is basically organized sound, and musical notes are sounds with specific pitches, frequencies, and durations. And each note corresponds to a particular frequency that's expressed in hertz. The scale that we are using in Muse is called the chromatic scale, and this is the scale that's been used in most of today's popular music. It is a scale that has 12 notes, and it looks something like this. This, as you can see, is a keyboard, and the 12 notes that I'm talking about here are running from, if I use solfege, it will run from C to C, and if I use the do to do, and I use the alphabets, it will be running from C to C. And this 12 set of notes, called semitones, added up together is known as one octave. The notes, the frequency of the notes are actually related to each other, and this relationship can be described in a mathematical formula. The frequency are defined around a standard pitch, which is A4, which in hertz is 440 hertz. Now, this is actually a ISO standard. So you can see from the slide, it says ISO 16:1975 standard. So this is a standard pitch, 440 hertz for the note A4. And notes that are of the same pitch, that is within the same pitch class, are in the same ratio, in the ratio of power of 2. For example, if A4 going up to A5, it would be half of that. Right? So let me show you a diagram of how that works. So if A4 is 440 hertz, sorry, not half, a double of that. A5 would be 880 hertz, and A6 would be 1,760. A7 would be 3,520. So the difference between the different notes, difference between the 12 semitones that is 1 octave is 2F, or 2 times of the frequency. Right? So if I just move one slide back, you can see that A4 to A5 is 2 times. So 2 times 444 hertz is 880 hertz. And that is described by the mathematical formula 2 to the power of 12 over 12 times F. Of course, if you talk about the difference between 2 semitones, then the formula is 2 to the power of 1 over 12 times F, the F being the frequency. Let me give you an example here. If I want to find the frequency as compared to A4, I will need to find the distance from A4. For example, C5 is 3 notes or 3 semitones after A4. So the frequency of C5 is F equals 2 to the power of 3 over 12 times 440 hertz, which is 523.25 hertz. So if I want to get a sine wave representing that note, what I do is I obviously use a sine function. So the sine wave S equals sine 2 pi F. We need to multiply the frequency with 2 pi because we are turning the frequency into radians. So how do I actually produce a sound? Now with the sine wave that I created, what I do is I take samples at regular intervals. Right? I take 44,100 samples over a period of 1 second. And you will see why it's 44.1K at a short while. And then from that, I calculate the wave value at each sample. I get a set of data. This is the Ruby code for the data. It's abstracted from Muse. So if you want to take a careful look at the actual code, you can go to Muse, and then you can clone the repository, and you can take a look at that. If I could just quickly go through here, so if I want to define the frequency of the pitch, frequency of a particular step away from the A4, so A4 is 440 hertz, multiplied by 2 to the power of the step, converting into frequencies divided by 12. And then I get that information. What happens is that it's produced into a stream of data. This data has, if you look at it carefully, it has a left. It has an array of 2 values. The stream has an array of 2 values, x colon x here. This is obviously the left as well as the right channel of the stereo. So the sound that I'm producing here now is actually stereo. Let's look at this. So this is a sound wave that's been produced, and you can listen to it. So that's the sound that's been produced by a sine wave, and the sine wave is that of A4. It's a pure sine wave. It sounds very digital. It sounds very mechanical. It's a pure sine wave. So how do we make music that's a little bit more natural? Right? So the sine wave is the most basic waveform, and it produces the fundamental frequency. And this fundamental frequency is a frequency that defines what the musical note is. If I want to create slightly different sounding sounds or musical notes, I would add waves at different frequencies and amplitudes, which is called harmonics. And when I add them up at the same frequency, different multiples of the same frequency, the note will sound slightly differently. Let's take a look at an example. say I have the y equals sine x wave, which is the blue wave here, and I add the y equals sine 2x wave, right? This will produce a wave that looks like the one below, the green wave, which is y equals sine x plus 2 sine x, sine 2x. This is the Ruby code that produces it, and this is the wave file that's being produced. Let's take a listen at this. Can you tell the difference between the two notes? I will quickly switch back to the previous note for reference. A little bit sharper, but still it's pretty mechanical. Let's look at something else. If I change the volume of the note over the duration, it will also change how the note sounds. And this is an example code that has been, this is the actual code that changes the envelope, which changes the amplitude of the sound wave over a period of time. And that produces these two waves. So by applying two different types of envelopes on the sine wave, the first is a sine envelope, and the second is a cos envelope, a cosine envelope, you would notice how each of these waves actually changes the quality of the sound. Each of these envelopes changes the quality of the sound. Let's listen to the sine envelope first. Did you notice that the sound started from being soft and it gradually became louder, and finally it tapers off to be soft again? Now let's listen to the cosine envelope. The quality changes again. So you have a loud sound and it tapers off towards the end. And if you listen to both of them again, you'll notice that the quality of the sound is quite different from that of the pure sine wave as well as the modified sine wave and the different envelopes that have been applied here. Let me try to play all of them again by going back in reference to the first sound that I played for you. The second one. And then the one with the sine envelope. And finally, the one with the cosine envelope. Now that we have produced the waves, we want to store them into files to create digital sound. And digital sound can basically be stored in either a compressed or an uncompressed format. Compressed being the very popular MP3 that we are all familiar with and the various variations of that. The uncompressed format, which is what I'm using, the main format is PCM. It's stored as either a WAV file in Windows or AIFF files in Mac. But of course, the WAV file being so popular, now it can be played in almost any computer. So you will notice what I've done so far. Basically, digital audio is a digital representation of an analog signal. Right? You would think a little bit about that. Basically, what I'm doing is I'm actually storing an analog waveform in digital representation. The WAV format is a audio file format for Windows, and it's derived from the RIF format, the resource interchange file format. Basically, it's a bitstream format that stores data in chunks, and the format is a linear PCM encoded format with 2 channels of 44.1 K samples per second. And now you can understand why I use 44.1 K samples in 1 second, and 16 bits per sample. This is the format of wave. You have the RIF chunk, which basically defines that this is a wave file. This is a RIF file. And then we have a format chunk, which talks about that this being a wave file, and the formatting of the file, whether is what kind of audio format it is, the number of channels, mono, stereo. It could go up to 4 channels, sample rate, byte rate, and so on and so forth. The data, actual data, is stored at the bottom. You can see the data chunk here. And within the data chunk, you will store a frame, and each frame will have 2 channels. In our WAV file, of course, in other WAV files, you would have more than other WAV files with more channels. You could have, say, a subwoofer channel, and then maybe you could have 3 or 4 different channels. But for our example, we'll have just 2 channels because it is stereo. If I open up the WAV file, this is how it looks like. It's a binary format. So how do I actually save the files in binary format using Ruby? Actually, it is a lot less difficult than you could imagine. You might imagine. You could use the very fundamental array pack, which basically writes the data into the file as binary, or you could read the file using string unpack, and it comes out with the data that you want. Of course, if you write everything using array pack, it could be pretty tedious. So what I've done in Muse is I use a library called bin data, which allows me to represent the WAV format easily. And then while I just pass it the data, it will stuff the data into a binary format that I've defined. The data is just integers, basically, representing the sample at different intervals in time. So this is the WAV format. If you remember earlier on, I showed you the riff chunk, the format chunk, the data chunk, and then I combine everything together in a WAV format. And within the WAV file, I will have different attributes. Here I store the riff chunk, the format chunk, and the data chunk. With that defined, I have a write method that allows me to write the data. If I pass in a data stream, which is essentially an array, I would then write it into the data chunk, set all the necessary parameters, and finally write it to a file and close it. So if I want to write it to a WAV file now, what I do is wave.new, file name, and then I pass it the stream data and .close, and voila, I have a WAV file. Okay, so now we are able to create a sound, create musical notes, assemble them together in a WAV format. Let's see how the code all assembles up. So here I have the notes that I define. So A, it's the musical note A, B, C. This is basically the chromatic scale. AIS is basically A sharp. CIS is C sharp. You notice for those musically who knows the musical scale that we don't see any flats here. That's because the sharps can be represented, can represent flats as well. So I just define only sharps. And the frequencies here are defined in the number of steps away from A4. So A4 being 0, if I go 1 semitone up, it will be AIS4. 2 semitones up will be B4. 3 semitones up, the example I showed earlier, is C5. If I go below, then it will be -1, -2, -3, -4, and so on and so forth. Right. The rest of the code is something you have seen earlier on. Finally, you write the WAV file, the data to a WAV file. Okay, now that we are able to produce the music and write it to a file, we want to create more than just individual notes. We actually want to create a song. And the best way of doing this, of course, this being Ruby, is to use a domain-specific language. What is a domain-specific language? It's something that's really popular in Ruby. It's a way of defining pseudo language that's specific for a specific domain. Primarily, it captures all the concepts of the domain. That includes the jargon. However, it is still Ruby, and that means it is still a program. So with Muse, I've created a DSL for writing music, but ultimately, the musical score itself that I've created is a piece of code. It's actually a piece of software. It's a program. The techniques I use in Muse in creating the DSL, there are many methods of creating DSL, but there are three primary techniques that I've used. Very popular techniques and very commonly used. The three methods and three techniques are, the first is using defining a DSL as methods in classes. So the two classes that I have are called song and bar. The second technique is to use instance eval to evaluate the musical score. The third is to use method missing to catch the names of the notes and chords. So the first, DSL are methods. If you look at the song class, basically the methods that are used here, song.record, Hotel California, harmonic, guitar, and so on. Record itself is a method. It's a static method for the class song. And I take in a block. And this block is being evaluated. Here I define a bar. And the bar itself has methods. So here you can use the bar directly .notes, and you can put in all the rest of the notes in here. Next, I use instance eval. The notes here, D4, E4, FIS4, these are actually methods. You will see B:2, basically this is a hash, B meaning the beat. So I'm playing the note D4 for 2 beats, then E4 for 1 beat, and F sharp for 1 beat. And the duration, the beats per minute is 100. Here, bar 1 means this is the first bar. So the notes for the first bar are E4 with 2 beats, E4 followed by F sharp 4. The final technique that I use is method missing. Here, of course, I could define all the notes individually as separate methods, but if I do that, I would not be able to create chords. So how are chords being formed? Chords are formed by putting an underscore between the notes. And how I do it is I will break it up. I will split up the string, and I will take each individual note and I will play all 3 of them together in method missing. If you take a look at the code in GitHub, you will see clearly what I mean. Okay, so I'm done with creating Muse. We are now able to create a sound, followed by converting that into a musical note, being able to vary the musical note, and finally use a DSL to define music using those notes. Let me show you another piece of music that's being created from this musical score, the Turkish March. I'll show this in MP3, but the original is a WAV file. Here it is. I'm using Audacity to show you the wave. Let me go a little bit deeper into it, a little bit in details into this piece of music, and you notice they are all consisting of basically sine waves. Let me play the music now. hope you like the piece of music. So I've talked about how we created Muse, but really Muse is not why. Creating Muse is not the end goal of what I wanted to achieve. In fact, Muse is a means to an end. I created Muse as a tool to do something else. And that something else is what I call Auto the Algorithmic Composer. What is algorithmic composition? It's a technique of using algorithms to create music. So essentially, what I wanted to do is to allow a piece of software to create music, not just transcribing the music from an existing piece of music or even writing a new piece of music, but allow algorithms, the computer itself, to generate music. An example of this is, say, I would grab a tweet from Twitter, and then I will create music from it. Or maybe I will scan a picture, get the data points from the picture, and create music from it. Or I could get today's weather report, and again get the data points and create music from it. So all these things are possible with Muse because Muse is Muse is a library, and the music that's been created out from Muse comes from a piece of program. So the musical score that is defined in Muse is actually a Ruby program, and you can do anything you want with it within the rules of a Ruby program. Now I will show you how I would do this by grabbing a tweet from Twitter with the hashtag RubyRR, and then I would generate the piece of music from it. Of course, the music itself is not exactly very pretty at this point in time because the algorithm I use is quite simple, and I will show you the algorithm that I use. But the concept is that the possibilities, the potential of creating music from a piece of program. Now, the algorithm is quite simple. What I wanted to do is have melody. I'll put in chords, and this will create music. First, of course, I need to grab the tweet from Twitter, right? Because the hashtag I'll be using today will be RubyRR. Then I split the tweet into words. And from those words, I convert each word into a number using the touch-tone keypad algorithm. So what's the touch-tone keypad algorithm, you might ask? It's basically this, which is something you're very familiar if you have used the keypad to write SMS in the older phones. So the keypad here and a word to number, very simple algorithm. Next, I find the 7 most frequently found notes within those words. So I create from each word. I convert each word into a note, and then I try to find the most frequent 7 notes. From those 7 notes, I will try to determine the musical scale, and I only use the major scale here. So it's actually a very simplified algorithm. Now, the major scale has one property, which is that each scale has an n number of sharps. So that's how I actually determine whether the notes belong to a particular scale. Basically, I find the number of sharps within that, or I find the number of sharps within that 7 notes, and then I would find the corresponding scale. Right. So, for example, the most frequent notes have 5 sharps. That will correspond to this scale. Now that I have the scale, I will get the chord progression for the scale. So I use a very, very basic, very, very common chord progression, which is 1, 4, and 5. And from there, I basically strum the chords. And I would have the chords. Next is the melody. The melody starts from the first note of the scale. So, for example, if I determine the scale to be this one here, then the scale here, number 5, then the first note would be B. So I determine the first note of the scale. Next, I calculate the distance between this note and the next note by using the number of too far away from the current note, so I just choose an arbitrary number, 5. After I determine how far it moves within the mod 5, I will determine whether it actually moves up the scale or down the scale, right? So this is basically a toss of the coin. Of course, it's not random. It's fixed. So I do a mod 2, and I determine whether it's 0 or not. If it's 0, then if 1 is not, then it goes down. And from then on, I try to find the number of syllables for each word. So within a word, I determine the number of beats. The number of syllables equates to the number of beats. So, for example, a word hello has 2 syllables. That means you will have 2 beats. Now that I know how many beats to play for the note and I know which note it is, I move from one note to the next. And I would have the melody as well as the chord. And therefore, I have the piece of music. Now, having that 7 notes and the chords as well, I need to break it down into 4 words per bar because I want to use the 4/4 time. And then I'll write it into wave file. This is basically the code that's been used to write that piece of music. Let me show you the demo. So this is the code. As you can see here, this is the keypad algorithm. And I use Twitter to do a search on the hashtag RubyRR. I will also print out the text. And then I'll calculate the number of syllables and do all the rest of the algorithms I just described earlier on to produce the music. Here, I would record the music into a file called Autobot Music. Right? So let me run this program now. As you can see, it is processing the music now. The tweet that I've gotten is basically the one from O'Reilly. It's creating the music, and it's writing to temporary files. In order to speed up the creation of the music, what I've done is I've parallelized the creation of the music into multiple files, and then I assemble them back together again. Now you look a little bit into how the files, the music is being created. The bar 0, I determine there's a note A that's beat as particular beat or particular octave, particular sound, and particular harmonic. This will be generated into a piece of music. I noticed there were some questions being asked, but if you just hold on, I will play the piece of music before we continue. So I combined the temporary files, and the total time taken is 1.3 minutes. It's done now. So let's take a look at that music. So that's Autobot music that's just been created. It's 1:45 a.m. here in Singapore. I will open up Audacity again, and let's take a listen to that piece of music that's been created from the tweet. what do you think of the music? Okay, let me switch back to the slides. So, of course, the auto as it is today, it's a toy algorithm. It's very basic. The music has been generated. It's not exactly very pretty. But, of course, I do plan to evolve Muse sometime. And what I really want to do is not auto, but Autobot. Right? Something much more sophisticated. So that's the end of my presentation. Here are some ways of contacting me. And while I switch away from the slides now, I will take the questions. How can you create a chord with some notes that last longer or end before others? So you can actually, so if you notice, let me open up a earlier file, the Hotel California piece of music. So you notice here, I have bar 1, bar 2 here. Okay, maybe Hotel California is a bit more complicated. Let me open up the Turkish March. Okay, so you notice the Turkish March, which is essentially this particular piece of music here, right? There on the over here in the first bar, on the right hand, I only have one set of notes. On bar 2, I have both left hand and right hand. So I have bar 2 here. I have 2 sets of notes. Right, so I can actually have more than one set of notes that's been played at the same time within a single bar. And that's how you actually do that. I hope I answered the question. How do you create a chord with some notes that last longer or end before the others? So you basically put them in the same bar, and then if you have the chords that last longer, then you will just continue. And if it's the same bar, then of course you need to put in the rest here, which is essentially an underscore. I try to find an example here. So here is an underscore. It's basically a rest. I'm resting for half a beat. Okay, I hope that answered the question. Let me move on to the next one. DSL domain-specific language is probably obvious, but just in case. Yes, so DSL is domain-specific language. Oops, I think I went the wrong sequence. I went from the question 5 backwards to question 2. Okay, how long did it take for you to record Turkish March? Okay, to create that piece of music itself, because I actually transcribed it from this score into this piece of code, it took me probably an hour. It is hard work to actually transcribe this. So the reason why I did this is because I want to show that you can actually create music from, and you can translate this from a musical score into Muse. But that was not the original purpose why I created Muse. Muse is actually created so that I can use software, I can use algorithms, I can create my own algorithms to generate music, not to create music from existing pieces of music. You can do that as I've done in Turkish March and as in Hotel California as well, but that wasn't the original intention. In fact, the Hotel California took me a couple of hours, which is pretty long. But of course, once that's been done, then music is pretty nice. Here, if you look at Hotel California, I have even defined things like chords that play a certain way, and then I can reuse them. The big chords are essentially methods. If you notice here, they are essentially a method. B minor 7. So I play B minor 7 here at the first bar, and so on and so forth. F sharp minor in the second bar, A major, E major 7, so on and so forth. Okay, by Greg Mazel. I like the tweet music. Is there a text file related to that tweet? Oh, yes. I probably did not show this very clearly just now. So the text that I highlighted here, that's the text. In fact, that's the tweet that came in just now by O'Reilly. I suppose no one else actually tweeted about this. So I got this tweet from O'Reilly, and I converted this text in that piece of music. Okay, next question, Xiao Gang Han. Is it possible, easy to create meaningful sound from text based on its sentiment or other semantic information expressed in the text? Yes, I think you basically hit the sweet spot that I wanted to achieve. Basically, I wanted to create music that can reflect someone's sentiment. Of course, that is not really inherent in Muse. That's probably inherent in whichever algorithm you use to create the music. For example, if you have an algorithm to detect the mood of that particular text, use some sentiment analysis to detect that this piece of text is sad, then you could play certain pieces of music that's sad. Right? Of course, you need to have music theory background as well. Say, how do you generate sad music? Do you use more minor chords, or certain kinds of way that you play music that make it sad? So you need to have a combination of the algorithm to detect the information from the text, as well as the musical know-how to create or compose music that corresponds to that piece of text. Okay, I hope I answered that. Okay, seems to be more questions. Okay. Do you include the harmonics package in Muse? Harmonics equals okay. Yes, it's all in there. I think the harmonics packages are not very complete. I've only done some experiments on it. It probably needs a lot more time and experimenting. Although I indicated that this particular harmonic is a guitar, another harmonics organ. If you actually use it, it does not really sound that much like organ or that much like guitar. That's how I wanted it to sound like. But it does take some time to experiment with different sine waves to make sure that it comes out to the correct sound. Right? Of course, things could be a lot easier if we use MIDI, but then MIDI does not actually produce things from the fundamentals. So, and that's how Muse works. Okay, next question. Do you know of any effort to use Ruby code to transcribe streaming audio as input and generate bar note output? So the question asked about doing the reverse, because what I've done basically is to transcribe manually, but I could of course transcribe it using a piece of, using another script. I could very easily, if any of the audience actually use Lillipond before, could actually convert from Lillipond to Muse. If you actually write the code to pass Lillipond and then convert that into music. I think the question is asking, is there any way of converting it the other way around, meaning taking raw music, streaming audio in this question, and then converting it into bar note output, which is basically Muse. So I do not know of any effort. The short answer is, but then, my code is open source. You can easily take it and do what you like with it. Okay, another question. Okay, all the questions seem to have disappeared.
Great. Sheong, we will say a very big thank you to you for presenting a really fascinating webcast for us all today. We thank you for sharing all your knowledge and expertise.
Thank you.
Folks that attended the webcast, we hope you enjoyed it and you benefited from it. We'd like to let you all know Sau Sheong's book, Exploring Everyday Things with R and Ruby, brand new title, brand new release. It is available today as the O'Reilly Deal of the Day. And what that means for you is you can get it today, and as a thank you, we're going to save you some money. Visit O'Reilly.com. Look on the right-hand side. You can't miss it. It's right there. And we also pushed out some details to you all in your group chat with that. Again, we thank you, Sau Sheong. Thank you, everyone. This will conclude today's webcast. Goodbye, everybody.